Yes, our next topic is electric field strength at a point on the equatorial plane or equatorial line of an electric dipole. So what is equatorial line? Equatorial line is a perpendicular to the axial line and passes through the center of the electric dipole length. So consider this is AB is the electric dipole. Here at A point, so we can keep minus Q charge, at B point plus Q charge. These are the separated by 2A distance. So this is center of the dipole O. So what is the distance? OA equals to A and OB equals also is A. So this is the axial line. The equatorial line is nothing but the perpendicular line. Okay, this is the perpendicular line to the axial line, passes through the center of the electric dipole length. Okay, this line is the equatorial line. So we can find out the electric field strength on equatorial plane or equatorial line at a point C. So we consider a point C is okay on equatorial line. The distance from O point, this is R. So then the electric field direction due to positive charge in this direction, and for the negative charge it is in this direction. Okay, the negative charge in this direction and positive charge, so this direction. So the total electric field is defined from parallelogram law of vectors addition. So this is the one side, this is another side, this is resultant electric field due to positive charge and negative charge. So then here, first of all, electric field strength due to positive charge at C point. So then it is E plus Q equals to 1 by 4 pi epsilon naught into Q by, so what is the distance here? BC square. This equals to 1 by 4 pi epsilon naught into Q by BC square equals to square root of R square plus A square whole square. Square root cancel, so then it is R square plus A square. So this is equation number 1. Next one, electric field strength due to negative charge at C point. So then E minus Q equals to 1 by 4 pi epsilon naught. So this is Q by AC square, that equals to 1 by 4 pi epsilon naught into Q by, so what is the distance? AC, R square plus A square, square root and square gets cancelled here, R square plus A square. This is equation number 2. So then the total electric field strength can determine can determine using parallelogram addition. Parallelogram law of vector addition. So what is the angle between these two sides? So this is angle theta and this is also angle theta. The total angle is 2 theta. So then, from the A is a vector and B is another vector, then the resultant vector equals square root of a square plus b square plus 2ab cos theta. Here E equals to square root of E plus q square plus E minus q square plus 2E plus q E minus q. So cos, what is the angle here? Total angle is 2 theta. Okay, so here this is equation number 3. But here equation number 2 and equation number 1, E plus q equals to E minus q. E minus q. Okay, so it is 1 by 4 pi epsilon naught q by r square plus a square. It is also 1 by 4 pi epsilon q by r square plus a square. So both are equal. So then E equals to, it is written as square root of E plus q whole square plus E plus q whole square plus 2 E plus q E plus q cos 2 theta. Okay, here it is written as E equals to square root of, okay, here is E plus q square plus E plus q square, 2 E plus q square plus it is also square, 2 E plus q square cos 2 theta. So what is common? E equals to 2 E plus q square is common, 1 plus cos 2 theta. Okay, so from trigonometric equations, 1 plus cos 2 theta equals to 2 cos square theta. So then it is written as square root of 2 E plus q square into 2 cos square theta. So from above equation, E equals to square root of, it is nice, 2 E plus q cos theta whole square. Okay, and square root gets cancelled. So then E equals to 2 E plus q cos theta. So this is equation number 4. So from triangle OAC, cos theta equals to, adjacent side is A by hypotenuse r square plus a square power of 1 by 2. Okay, this is equation number 5. Equation number 1 and 5 are substitute in equation number 4. Okay, so then it is written as E equals to 2 divided by 4 pi epsilon naught into q by r square plus a square into cos theta equals to a by r square plus a square power of 1 by 2. So from this equation, so 1 by 4 pi epsilon naught into 2aq divided by r square plus a square power of 3 by 2. Okay, 2aq is nothing but dipole moment. So then E equals to 1 by 4 pi epsilon naught into p by r square plus a square power of 3 by 2. This is equation number 6. Okay, in this equation number 6, if the condition is r is greater than and greater than a, then a square is negligible because r square is again greater than a square. So then a square is very small. Then E equals to 1 by 4 pi epsilon naught, so the term p by r cube. So this is the electric field strength at a point on equatorial line due to the electric dipole. Okay, next we consider here the point is the total electric field. The total electric field is the total electric field strength E is opposite to P bar. So then we can take E bar equals to minus of 1 by 4 pi epsilon naught into P by r cube into P cap. So then E bar equals to 1 by minus of 1 by 4 pi epsilon naught into P bar by r cube. So this is an equatorial line. The total electric field strength E bar equals to minus 1 by 4 pi epsilon naught P bar by r cube. So here, since P bar equals to P into P cap. Okay, so this is about the electric field strength on equatorial line at a point C. E bar equals 1 by minus 1 by 4 pi epsilon naught P bar by r cube. So next, our next topic is physical significance of electric dipole. So here, so we know that the dipole is nothing but the two equal and opposite charges is placed at a distance. For example, it is plus q, it is minus q. Here it is point A, point B. It is placed between 2a distance is called the electric dipole. Okay, now, so what is the importance of electric dipole? What is the physical importance? What is the physical significance? Significance is nothing but the importance of the electric dipole. So now, some of the molecules, so in most of molecules, the center of positive charge and negative charge lie at the same place, lie at the same place, then their dipole moment is 0. So here, for example, we consider carbon dioxide and CH4, methane. So for example, carbon dioxide, in the carbon dioxide, C, the structure is C, and it is placed like here, it is oxygen, and it is a form of oxygen. Okay, here it is consist plus 2q, and it is minus q, it is minus q. Okay, the dipole between minus q and plus q, and dipole between minus q and plus q. So here equal charges and opposite. So here the center of mass between oxygen and carbon is this point, and the center of mass of this point, carbon and oxygen, is this point. So then it is produce the P1 and it is produced at the P2. Okay, so P1 is a dipole moment and P2 is the another dipole moment. So both are equal, both are coincide each. Okay, so these center of positive charge and negative charge, it is both are coincide, so both are equal distance here, and it is also equal distance. Then the dipole moment, total dipole moment equals to P1 plus P2. So both are equal here, so P1 equals to P2. So then total dipole moment, so in opposite direction. Okay, it is in this direction and it is in this direction. It is like this direction, it is like this direction, because so the dipole moment from positive charge to negative charge, and here positive charge to negative charge. So then it is like this and like this. The total dipole moment P1 plus P2 equals to P1 bar minus P1 bar equals to 0. The total dipole moment is 0. So but here in carbon dioxide or another one, methane also. So here it is methane. In this methane, this is plus Q, this is plus Q, this is also plus Q, this is also plus Q. So it is consist minus 4Q. Okay, carbon has minus 4Q. So the center is here, the centers are here. The total dipole moment of this methane CH4 is 0. But carbon dioxide and methane are types of molecules. They develop, okay, they can develop the dipole moment when electric field is applied. So when electric field is applied, the dipole moment is developed. Okay, the net dipole moment is developed. For example, we consider this is an external uniform electric field. In this uniform electric field, this is uniform electric field. electric field intensity is E. When we keep here the carbon here and oxygen, this is here oxygen. Before the electric field applied, the center is here and the center of mass is here. It is okay, it is negative and it is plus 2q, it is minus q. So the direction of the dipole in this direction, so it is the dipole from positive to negative and negative to positive. Okay, it is negative and it is positive. Okay, oxygen is moves like here and here, sorry, it is moves like, and here oxygen moves like here. Then after the dipole, so carbon is like oxygen is here and this oxygen is moves a long distance. Then the center of the center of masses doesn't coincide. Then here the dipole moment is developed. When the electric field is applied, okay, what happens before the electric field is applied, the center of mass are coincide. But after the electric field applied, then the dipole moment is moves oxygen, this oxygen moves in this direction and this oxygen is moves in this direction. Okay, the carbon is at constant position, so negative and this negative is moves and oxygen is moves like in this direction, the distance is decreased and this distance is increased. The center of masses are like doesn't coincide, then the dipole moment is developed. This is permanent dipole moment. So but some molecules, okay, here these molecules are called non-polar molecules. Non-polar molecules. In the non-polar molecules, carbon dioxide and methane, when the electric field is applied, the dipole moment is developed. So some molecules, the center of masses, the centers of negligible and the positive charge do not coincide with negative charge, therefore they have a permanent electric dipole moment even in the absence of electric field. In the absence of electric field, permanent electric dipole is developed. Such type of molecules are called polar molecules. Okay, in the polar molecules, permanent electric dipole is developed. In the absence of electric field. Okay, so for example H2O, water molecule. So here oxygen is here, the hydrogen, this is hydrogen, this is another hydrogen. So it is minus 2q, so it is plus q and it is plus q. Okay, this is center of mass, this is also center of mass. but here the center of mass and center of mass, then the total dipole moment is developed due to the polar masses. Okay, so here in this between, for example, it is P1 dipole moment, so it is P2 dipole moment. So in between the angle is 104 degrees. Okay, for example, in parallelogram law, this is P1, so here P2 side and P1 side, and these are two sides. The total dipole moment, so for example, this is angle 52 and this is 52. So for example, it is theta and it is theta. So then what is P1? P1 equals to, okay, so P1 or P equals to, sorry, P equals to P1 cos theta, and also it is P2 cos theta. It is consist certain angles, cos 52 degrees and cos 52 degrees, both are in same direction. So then it is not equals to, so then the dipole moment is developed. This is about the polar molecules. It is called the polar molecules. The polar molecules, in the absence of electric field, permanent electric dipole is developed. Such type of molecules are the polar molecules. In the non-polar molecules, in the absence of electric field, the total dipole moment is zero. When the electric field is applied, the dipole moment is developed. Such type of molecules are called the non-polar molecules. This is the end of the class. Next class we will discuss the Gauss law, applications of Gauss law.